You can find like all
I don't think you're the only one.
And then I'll do a new share of desktop 2.
You can put a little line and then as you can my day is so just put it on.
Yeah.
I have all the results in my computer, so come with a USB key or
Okay, perfect. All right, yeah.
So it's noon. Do you wanna? Who's gonna introduce Sangeeta and Melissa? Can they introduce, or should I introduce, or should they introduce themselves?
I can introduce myself, I don't mind.
You think? Yeah. Why don't you introduce yourself? Because everybody here knows you guys pretty well.
Yeah, and I think we've at least met the folks at Auburn. All right, welcome to this week's Neuroimaging Journal Club. I'm William Monroe. My buddy
Ravi.
Ravi is here with me, and we're from Research Computing. And so my role with Research Computing, for those of you who may not know, is that of data scientist. So I help researchers take their data and make stories out of them. Some universities call that computational science, some call it research facilitation, but what it boils down to is if you've got a lot of data and you don't know what to do with it, or you're having a hard time getting your processing done efficiently or quickly, that's what I come alongside and help researchers do. Ravi, do you want to talk a little bit about what you do with the cluster?
Yeah, so I work as a software developer with Research Computing, and I help neuroimaging researchers. I've been a part of the Visual Brain Core for the past 3 years.
I think it's 4 now.
It's 4, yeah, so for the past 4 years. And we have office hours upstairs every Monday morning. And so I help work with neuroimaging researchers over there and get their workflows ready to be run on the HPC system or the Chia cluster. And other than that, I help researchers install their softwares on the cluster so that all the softwares that they need for their workflows, I install those, and yeah, that's basically it.
Today what we're talking about on a broader context is something that we've started calling UAB's Data Science Club. So data science is, like I said earlier, the science of taking data and making stories out of it. It's stuff that you guys already all do. But data science is the current cultural buzzword that also includes not only statistics and traditional analytical techniques, but also machine learning. And so all of you have the technical wherewithal to be able to do some basic programming at the least. I know some of you in particular do some pretty advanced programming. And so there's no reason why you shouldn't be able to do machine learning. But machine learning today is where HTML programming was in like 1997. If you didn't have like the big, thick, like 1,000-page book and you hadn't gone to the course, it was like reading a language that you're just totally unfamiliar with. But if you did take those courses, it was pretty straightforward. And so what Ravi and I are trying to do is help bridge that gap between the analytical techniques that everyone here is perfectly smart enough to be able to use and that language barrier for actually using it. On the flip side of the coin, engineering has a language problem of they don't understand how to talk to applications folks. So electrical and computer engineering or computer science are all learning these techniques, but if you went to an electrical engineering or a computer science professor and just described your problem the way that you think about it, they might have a difficult time bridging that gap to try to figure out how to apply their techniques to your problem. And so by making this data science club, we're hoping to kind of bridge that gap, help folks on the engineering and computer science side work on applications, and then help the applications folks do enough of the technical data science work so that we can have those conversations on a more regular basis, because that's where all of science is going right now. So on a very practical today kind of level, we are going to be looking at using machine learning to denoise images. And at the end of today, I mean, if you have your laptop, you can follow along. If you don't, we posted the GitLab link to this in the, Sangeeta sent it out in the email. And we're recording today's video on our YouTube channel. It's streaming on YouTube Live right now. And so you can go back through and follow the video later with the code and kind of get a feel for what it takes to actually run this. And at the end, we'll also show, like today, we're going to be working on pictures of handwritten digits. But there's a really similar example that's really straightforward using MRI images that is on another tutorial website. So we'll share the link to that as well. So if you guys are interested in how this particular technique might apply to MRI imaging or the types of imaging that you guys work with, you can at least see that it's pretty generalizable. Any questions so far? All right. We got the resources set up for today. The whole workflow is going to be on Chiha, the UAB high performance computing resource. If you go through the links that were sent out by Sangeeta, it'll walk you through how to set up your machine learning environment, which was the first video that we put up for this data science club, was how to get your machine learning environment working. For folks that don't have access to Chiha, I think everybody on this, that can hear this has access. But if you don't, you can still use that environment. You just have to install Anaconda on your local machine, and then you can build the environment from the environment file that was sent out earlier. But today we're going to be looking at something called building autoencoders with something called keras. So let's just go through real quick how you would get this code on your machine or in your space on Chiha. So we have it set up so you don't even have to do any SSHing or any Linuxy type things. You just have to copy this script here and click here, and it will take you to the UAB job composer. So this is actually a website portal that Research Computing has set up that you can access the supercomputing resources directly from Chrome. So you don't have to SSH in a terminal. You can just open up Chrome and here it is. And so what we're going to do here is create a new job from the default template. And then I'm going to scroll down and I'm just going to open the editor here. And I'm going to copy and paste the stuff from that GitLab right here. So what this is doing is making a directory that is shorthand for Research Computing Data Science Club, and then inside of that, it's going to download the files from this GitLab repo into a folder called Building Autoencoders in Keras, and if the folder's already there, then it will just update the code that you have. So if you happen to, see this really early on when I was making it, and then you want to come back and update your code, you can do that with this same bit of code. All right. So now I can come up here and I can click submit, and that should run. Yeah. So now it's running. And that really shouldn't take much time. Yeah, so it's already completed. And if we go down here to this slurm.out file, we can look and see what it was actually doing. And apparently I got some errors here. So we'll have to troubleshoot that a little bit later. Not sure why that happened. This worked earlier. Yeah, of course, whenever you do a demo, it doesn't work exactly right. But that's also part of, this is actually fortuitous that this happened during this, because code never works the way that you want it to, right? And so that's part of why Ravi and I are doing this, and part of why we want to do this for you guys and for our research environment here at UAB and with our folks over at Auburn, because all of you know us, you have our email addresses, you've come to our office hours. And so if this happens to you while you're trying to do one of these and you're like, man, shoot, I was really hoping to get this working, you can just come to office hours and we'll help you troubleshoot it. So that's, it seems like a bummer during the demo, but this part of the demo is the fact that sometimes things won't work and you can come to office hours. I believe I already have this code downloaded, so we can just keep going. I will work on fixing that script so that that doesn't happen to you. But if it does, just come to office hours or send Ravi and myself an email and we'll get it going. Or if you're watching this on YouTube later, you can put a comment on the YouTube link and we'll get back to you there as well. All right. So now we're going to go down and we're going to see how can we actually start up this notebook so that we can start doing this work. And so again, we're going to go back to the UAB portal for the supercomputer, Research Computing on Demand. And we're going to click on Interactive Apps. And you can see here that maybe the last time you looked at this just said Jupyter Notebooks and R. And now it also says MATLAB. So if you guys didn't know, we also have MATLAB on the cluster. Well, we've always had MATLAB on the cluster, but now we have it here so you don't have to start up the HPC desktop and then request a compute node and then load the module. Now you just click on that and it'll start you up MATLAB on the supercomputer inside of Chrome, which is really useful.
You younger students have no idea how lucky you are.
We are working really hard to spoil our user community. So if you don't feel spoiled, let us know and we'll keep on working on it. If there's other applications that you think would be good on here, that's also something you can let us know, because Ravi's been working on some generalized templates for adding new apps easily to here.
What versions of MATLAB? Because I know I can't use the R one because I need a different version of R.
So
it has all the versions of MATLAB that we have on the cluster.
Now, when you move on to postdocs and elsewhere, you may not necessarily get this kind of pampering, FYI.
And by the way, not necessarily means no way.
Yeah, I mean, for reference, I talked to a new radiologist here at UAB who came from the University of Texas system, and they have a much larger supercomputing group than we do, but it's not as user-friendly. And so even though she came from an area where there were a lot more computing resources, we really try to go the extra mile to make sure that the resources are usable by our researchers, because otherwise there's no point.
And I want to underscore that at other universities you would not get this kind of connection to the people that are doing this. We really appreciate it and want it to keep going. So say thank you as much as you can and tell your PIs how awesome it is.
Yeah, and if in your particular labs you need us to come and do a demonstration of any of this stuff, we're happy to do that. But continuing on with the demonstration. So if you come down here, this will show you which parameters you need to set for this Jupyter Notebook. So we need to load CUDA because we're doing machine learning, and I don't know if you've heard, but we need to use the GPUs generally to use CUDA. And to do machine learning stuff, GPUs work really fast for doing that, because even though they were created for doing graphics processing for video games, essentially, graphics processing is nothing but a lot of matrix multiplies, and that's what you need to do for machine learning. And so that's why using the GPU nodes on our cluster makes things go a lot faster. And a little plug for those, right now they're generally a little bit underutilized. So if you request a Pascal node for doing this work, you're not going to be sitting around waiting for a GPU to show up. You'll get it pretty quickly for you to be able to do this machine learning stuff. All right, so we're going to copy. I think I actually already have it in there, but we'll go over. And so we'll copy and paste it in here. And then as is specified here, we need to change this notebook directory because this is where Jupyter is going to start up on the cluster. If we don't specify this, it'll start up in our home directory and we won't necessarily be able to find our notebook. And so you need to make sure that you specify which directory you want to start it up in so that you can actually get to your notebook. And then for the partition, we're going to specify Pascal nodes. So I think most everybody in here is familiar with setting your partition to, express or short, medium, long. The Pascal nodes is a partition that specifically says, I want to go onto a node that has a GPU on it. If you were doing this from the command line, there would be another argument you would need to specify for how many GPUs. Right now, the default is if you ask for Pascal nodes, we'll give you 1 GPU for your Jupyter notebook. And so we'll go to here so you can see I have that set. And we're just going to do an hour. And Pascal nodes, this isn't a very big example, so 1 CPU and 4 gigabytes of RAM should be fine. And so we're going to go ahead and launch that. All right. And you can see it's already booted up, so we can already connect to it. Like I said, the Pascal nodes we're generally pretty quick about getting that out because we want everybody to be able to use them. All right, so now we can open this up and we can click on our notebook, and here it is. And now we're already programming in Python. So I know last week we had the discussion with, I can't remember her name. From Miami, and she talked a little bit about Python tools for doing meta-analysis across publications on things. So these are the types of tools that she's using. She's actually using a programming language called Python, which is actually a play on words from Monty Python, I think, is originally where the name came from. So it actually has less to do with snakes and more to do with British comedy, which is very in keeping with the computer science nerd thing. So as we go through this, we'll just kind of talk about what it is that we're actually doing. First things first, we need to import some libraries. Actually, before I get that started, so earlier we talked about environment. You can see up here at the top and over here where it says kernel, I can say change kernel. If you go through that tutorial to get your environment set up, you're going to create an environment called NBOTW, which stands for Notebook of the Week. And so that's the environment that we're using for this. If yours starts up and it doesn't say NBOTW up here at the top, you can just go in here to kernel, change kernel, and change it to NBOTW, and then you'll have all these Python libraries installed in your environment. All right, so in Python, this is how you import them. And so this is all code that somebody else wrote that we don't have to, which is great. And so we can run this by clicking this little play button here. And the little star says this cell is running. And so you can see it saying that it's using the TensorFlow backend. TensorFlow is a Google Python library for doing machine learning stuff. And they've really worked along with this keras library to make it really straightforward. So it seems like the machine learning part should be hard, but the hardest part about this is loading your data in, transforming it to how you need it, and loading your data out. And you'll see the machine learning model here is going to be less than 20 lines of code. So up here, this is all data stuff that we're doing. So this keras has a function called mnist that pulls in all these images of handwritten characters. There's other ways to load in your data, but for this example, this is really nice. It's a really straightforward way to load in some sample data. And so when we load that in, we're going to load some of it into a variable called train and some of it loaded into a variable called test. you always want to have a training and a testing database, because you don't want to create a machine learning model that uses all of your data, because then what you've done is you've essentially taught it to just memorize the data that you gave it. So we know from statistics and regression that if you have a series of data, if you use y equals mx plus b, that might not fit your data very well, right? Your r squared might be like 0.5 or less, and that might be really good for y equals mx plus b. If you use y with a polynomial of like x to the 8th, you can fit your data really well. But if I bring you another set of data, that function's not going to be useful, right? And so we call that overfitting. In human beings, we call that conspiracy theories, right? We go to the kitchen to get ourselves a drink. Our partner says, "Hey, could you grab me some popcorn?" We didn't hear it because the ice maker was too loud. We get back and they're mad at us because we didn't bring them popcorn, because clearly we heard them, and now they're mad at us because they didn't have enough information, but they made a decision based on that, right? And that's what machine learning models do. And it seems like this is a little bit of a tangent, but this is actually the way that these a good way of thinking about how these machine learning models work, right? If you don't give it enough information, or you give it too much information, you can set up an environment in which it will overfit, and it will give you a conspiracy theory about why something is the way that it is. And there have been very many examples of somebody training a classifier to decipher this is a dog and this is a cat. And what they've really learned is what grass looks like. And they call that a cat because all of their pictures of cats happen to be cats on grass. And all their pictures of dogs happen to be dogs that happen to not be on grass. And they thought they trained a really nice classifier for dogs and cats, but all they learned was what grass looks like.
And so now if you give them an image where a dog is on a grass, it's going to identify it as a cat.
Yeah. And so just like statistics, where you have a t-test, your distribution has to be normal, in machine learning, there's things like that you have to do to make sure that your analysis is robust. And that's kind of why we're trying to have these conversations with folks, because we're all going to be dealing with machine learning. You've all started to read papers with machine learning in it. And you've probably come across one where they say, we have 100% validation or 100% training accuracy. And if they have 100% accuracy, you know that their model is baloney, because they haven't done this simple part that's at the beginning of this simple example, which is separating their training and their testing data. Yes?
So you gave a really nice example of not enough information. That you said it's just as common to have too much information. Can you give an example of that?
Yeah, so in the sense of too much information, that's not exactly clear. It's better to say too many parameters to decipher the information that you have. Right, so just like with the polynomial fitting example, if you use x to the 8th, you have too many parameters to create a generalizable model. And so what ends up happening is if you specify a very large machine learning model and you train it for a long period of time, then it will just use all those parameters to tweak and just kind of memorize each data and go, okay, well, this one was this and this one was that. And so like even if you have a patient identifier in your image and you're trying to learn some pathology thing, it will most likely learn those numbers at the bottom rather than learning anything about your image, because those are a more reliable classifier of who was what. There have also been situations in which a machine learning model has learned which scanner was which, because folks that had a pathology were generally in the emergency room, which was a different scanner than the research scanner, which had the healthy controls. And so that's why, that's kind of an example to that level. Yeah. So again, we're doing matrix multiplies with this data. So we end up taking it in and reshaping it so everything's the same size. And then what we're doing is denoising. We're starting out with really clean images. So we're going to add noise to some of the images first. And so let's look at some of those noisy images. Sometimes Python doesn't spit out your plot the first time around, so if you just run it a second time, it'll pop up. So you can see we have these digits, and they're pretty noisy, right? Some of them are even a little bit difficult for us to read and see what it is. Like, is this a 5 or is it a 6? Is this a 7 or is it a 9? Is it a hippocampus? So yeah, so now what we're going to do is we're going to create our machine learning architecture. So like I said, this really is the smallest part of our code in a lot of ways. Again, we're going to import some more libraries. These are the functions that are used to create it. And at the most basic, we have to tell it what size our input is, which is the size of the input images, and what size our output is. And then we got to tell it what operations we want to do in the middle. And it used to be that when you wrote these programs, you had to specify, I want, this neuron attached to this neuron, attached to this neuron, and do all that kind of hard-coded manually. It was a lot of code. It was a lot of work. But now you just specify, I want a convolution layer with 32 filters, and it does that all in the back end and wires it to the next layer, and you don't have to worry about that stuff. So it makes it really, really straightforward. You guys have all dealt with convolution, right? Okay. So this is the.
Does everybody actually? Is that a real yes?
Okay. All right. I'm getting some honest answers here.
Okay.
All right. So convolution is simply the act of taking a filter and passing it over your image, right? So if you ever do Gaussian filtering of your images to smooth your data, or median filtering, you've done convolution and you just didn't know it. Because what you've done is you've taken a small filter, pass it over the whole image, and then it returns a new image. You can also do edge detection with convolution, where you take an edge detection filter, pass it over your image, and then it returns you a new image that shows you more clearly the edges. So one of the big advances in neural networks in the past 7 years has been this notion of, well, why do I do all this feature engineering? Why don't I give the neural network the capacity to learn these filters on its own? So if you break out these convolution layers, what's happening is it's actually learning an edge filter and a median filter and things like that correspond to the features in your image. But specifically, the type of model that we're building here is something called an autoencoder. Let me come here because I'm going to show you a diagram of an autoencoder. All right, so that looks like every neural network diagram that anybody has ever seen. It's circles with arrows going from one end to the other. But the interesting thing about an autoencoder is it is trying to recreate the input data from high-level features. The way that I like to think about it is it's kind of like a police sketch artist, right? So a police sketch artist has seen a lot of people. They've taken a lot of art classes where they've had to sketch real people. And then what they've had to do is then take classes where they've had to sketch people from just high-level descriptions. They had dark eyes. They had curly hair, things like that. And that's what our neural network is doing, is it's taking the input image and breaking it down into something that's called the bottleneck layer, or the high-level features, where at this point it doesn't have all of the pixel data. It's downsampled it enough that it's really just dealing with the high-level features. It's got 5 edges here and things like that, and then it's trying to recreate that input data. So the nice thing about this is, at first blush, that sounds really boring. Why would I want a computer program that spits me out the same image that I gave it at the front? Right? That just sounds kind of dumb. And that's the way that I felt about it at first. But the cool thing about autoencoders is I can tell the neural network, this is my input image, and this is the same input image on the outside, or on the output, and train it that with a differential between the input and the output. So I can give it these noisy images as an output and tell it that the clean images are what these images should look like, and it will learn that differential, and then in the future, if I give it a noisy image, it'll clean it up. All right? Does that make sense? Ravi, did you want to add anything?
No, yeah, I mean, basically that's it. So if you want to think about autoencoder in another way, it's just basically decompressing your image. It's taking out various features in the image, and then compressing and then decompressing the image again so that you get the input image.
Yeah, so just like we've also all interacted with, if you're taking research data, you don't use JPEGs, right? Because that's a compression format, that's a lossy compression format. And so when you put that image in a journal and they blow it up, you can see the areas in which the JPEG compression algorithm fiddled with your image and took out some of your actual data. We're doing a similar process here, except it's more generic, and we're using it as a way of analyzing our data instead of just compressing it for space purposes.
Yeah, and don't throw out the tar or unzip yet. It's just good for the compression is just good for the images on which you have trained, but it's not going to be useful in general.
Yeah. All right. So this is our machine learning model. So it comes with two sides, an encoder and a decoder. So you take your input image, you break it down into the high-level features, and then you take those high-level features and break it back out. So again, it's another example would be it's like a game of telephone. And so we've all known how that can go horribly wrong, or in many instances, the purpose of the game of telephone is to make something funny out of something mundane, right? And so that's an autoencoder for making something funny out of something that's just a normal sentence. And in here, we're making something clean out of something that was noisy. And so now that we have this, we're going to train our model. And so again, this is something that uses stochastic gradient descent, it uses backpropagation, it uses validation, it uses callbacks, it uses all these complicated words that we've all heard. We all might have a kind of a mathematical feeling for what's going on. But the nice thing is modern machine learning libraries don't make you do any of that. You are just saying, I want to use my model, I want to fit my model, I want my input data to be the noisy data, I want the output data to be the same data but not noisy, and then I'm going to train it for 20 epochs. An epoch is one view of all of my data. So if I have 60,000 images and my batch size is 1, then an epoch is going to have 60,000 iterations inside. Here, my batch size is 128, and my database is like 60,000. So I've got 2 orders of magnitude less. So I'm doing like 6,000 iterations per epoch. And so it's just a way of keeping track of what types of iterations I'm doing, because there's a lot of iterating involved. And then like earlier where we talked about validation, we want to, each time we want to test our network on a database that we know the actual answers. So for the validation, every time it gets there, it will run the noisy data through the network and then subtract that from the test data and see what the loss of information was there. And that'll give us a feeling of how generalizable our model is. And so and then after we fit our model, we're going to print what those training steps look like. All right, so you can go here. And this is the part that you really want a GPU for, because a GPU is what takes these images and does the matrix multiplies on them to propagate them back through the network forward and backward very, very fast. So we'll take a look. It takes a little bit to get set up, and then it goes. So how many of us have codes that run through 60,000 images in less than 3 seconds? I mean, these are really small images. I'll give you that. And it's hanging there. We'll see. Sometimes this happens where it hangs a little bit and takes a little bit to get going.
You can fill the void. Well, you got a question.
Yeah.
So in the beginning, you separated out your training data set and your test data set. So, we see these papers where they had 100 people, and so they take a proportion as a training data set, a smaller proportion, and then it's a larger proportion for the test. Is there some known quantity that you need for your training data set, either whether it's a proportion of your total or whatever the case may be?
So that's a really good question, and the answer is no. There is no defined, there's no definitive answer for you should always have 10% of your data in one pool versus 20% in another pool versus 80% in another pool. And I know I just added up to 110%, but sometimes people do that anyway. So just like in statistics, right, there's all different types of cross-validation that you can do, right? There's leave one out cross-validation, there's I'll hold this group out cross-validation, and then there's things where you'll take 80% and 20% and then shuffle those groups around, and then kind of take the average of all of those as your true validation set for what your actual generalizability is. And the same thing applies to machine learning. Just because we're doing machine learning doesn't mean people have gotten any smarter about how to do that data separation. And in fact, because the models are so complicated, people often forget to even do it, which is why it's really important to make sure that as a community, we're rigorous in doing it, and we have at least best practices, right? So if you have 100 images, that's not a lot for machine learning. So maybe you hold out 10 for your validation set, and you keep 90 for your training set. And again, maybe you do a fold-based cross-validation where you run your machine learning on the 90 and test it on the 10, and then you run it again on a different version of the 90 and a different version of the 10, and then you average those validation accuracies. So you see how your machine learning model in general would work if you had more data. Those things are all acceptable ways of dealing with the problem. The most important thing for these basic conversations is just to at least do it. At least separate some data out that your machine learning model will never use to update its model, because then you'll have a good picture of, is it actually going to work? And at the end of the day, that's what we really want. We don't just want nice publications. We want stuff that's actually going to work.
Yeah, and that concept of separating out training and testing data set is very important in machine learning, because otherwise you'll start getting those 100% accuracy of machine learning, which should not be there.
Yep.
So,
Yeah.
Just in case I'm wrong, it seems like for the autoencoder, you actually have to know what sort of noise you're expecting beforehand for it to actually work right, since you're training it on the noisy data and what it's supposed to look like.
You don't have to necessarily have a good function for what the noise is,
Okay.
right? So canonical data removal really does a lot of work to model the data, model the noise with math, so that you can figure out how to remove it. In situations where you don't have a good mathematical model for the noise, but you know how to take data with and without it, you can still use this technique.
Yeah.
So like MRI is a great example of, there's going to be lots of situations where like the technician took a phone call and the room wasn't shielded properly, and so something happens, right? And we don't know what that is. But as long as we have enough samples of like a person with and without that same data, ideally it's the same subject, right? With that noise, without that noise, then you can train a model to do this, even if you don't have a good mathematical model for what a cell phone during an MRI looks like. You can see it, you can repeat it, and so you can theoretically generate enough data to do this. Another thing in MRI is like the bias field, right? So if you take an MRI and you have a very slight motion drift, then over the course of time for like a functional MRI, your volumes through time will look a little bit different. And so theoretically, and this is something I'm in talks with Mark Boulding to figure out, is, all right, so we know how to take data with that and without it. And so since we know that, we can run the noisy data through and map it to the clean data, and we should be able to remove that, even though we don't have a good mathematical model for what that noise is.
Okay.
But we know that it exists.
And once we get those algorithms or the machine learning modeler, we can pass some other noisy data and it should clean up in the same.
Yeah. So this is the plot of the model loss. So this is the metric that we use to optimize our network. And so as we would hope, it gets smaller over time, because that's what we're trying to do. We're trying to minimize this particular metric. And so now we can look at how we did. And so this is basically the output here. So this function here, so up at the top, this keras gives us the ability, so once we've trained the model and we fit the model, we can just access another function called predict. We can put in data that it hasn't seen before, and then we can ask it to show us those images. And so here we go, autoencoder.predict, and we're going to predict on the noisy test data. So this is data that our algorithm didn't see when it was training. It only used it for that validation accuracy, but it didn't update the network weights based on that. And then we're going to take the first 10, and we're gonna look at those. And so we're going to set up our plot. There's going to be 20 spots in the plot, and then this is just, again, this part is just setting up the axes. It's a 2 by 10 plot, and I want you to show me, so this is a for loop that loops 10 times. I want you to show me noisy image I, 1 through 10, and make sure it's in the appropriate shape. And then I also want you to show me the predicted noiseless images from the network. And so then that's what it spits out. So you can see here, this is a pretty powerful technique, and we didn't do any median filtering or anything like that directly, but our neural network kind of learned those filters on the back end on its own. You can also see that all in all, this code is, I think, less than 100 lines. This is something that each and every one of you could, you can do. And so I would encourage you guys to, play around with this example and try to do this on your own. Do you guys have any questions about this code?
It said there was a comment up there to not ask why you're using Matplotlib.
So that is a good question. It's up here. I honestly don't know why that's in there. We pulled this example from the keras website, and that was a comment that they had in there. In the places where I've added comments, I've put my initials there so that you know that I changed something about this line, Because if you go, let's see.
I mean,
If-
one reason for that comment is that matplotlib is the most common plotting library available on Python. So
Yeah,
code will, like,
it's
just
kind
a
of
common, so just use
yeah.
this.
Okay.
Yeah. Yeah, I think because it's a tutorial, like Ravi said, they just didn't want to have to explain that piece because it's just, normal Python thing to do.
Yeah. Okay.
But I
If you
believe-
go to the link on the GitLab back, there's even more examples of using these autoencoders on this one.
Yeah, I believe there is ggplot as well now on Python.
Yeah.
Melissa talked about it in the research computing tutorial thing. So
Yeah.
maybe that's something that you can use as well.
Yeah, and there's also a library called Seaborn, I think, which is also another visualization tool. So the other thing that I wanted to show you guys is, and this was a tutorial that we thought about doing, but it's a lot more complicated from just the getting it to work standpoint. And I wanted something that we could get to work here in less than an hour pretty easily. So if you come here to this data camp community tutorials reconstructing brain images using deep learning, if you scroll through this code after working through that keras autoencoder code, this will be eerily similar, except now we're operating on three-dimensional MRI images instead of operating on two-dimensional digit images. So if you scroll down here, they're actually using data in this from the Human Connectome project. So a lot of you probably have this data already in your data folder on Chiha.
By the way, it takes up a lot of space. Maybe we should be sharing it.
Yeah. Yeah, well, and that was the other reason for wanting to do this on the keras or the MNIST data set, because that's very small. And to just get this tutorial working, you have to download like 30 gigs worth of data. And I knew that we already have it somewhere on the cluster. It's like, okay, I don't really want to get a room full of 30 people and say, okay, everybody download 30 gigs of data right now. So yeah, we're not going to do that. But if you come down, similarly, you have the setup of your importing Python libraries. Here, they're importing everything at the beginning. In my Jupyter Notebook, I try to import it close to where you're actually using the function so that you can see that correlation. And then we're loading data. This is a nice tutorial because it actually loads data from your hard drive. And so if you're following this, you can edit these paths in here to actually make it work for your data. And so then you can go through, and this is just, again, this is data setup, getting the data into the right shape, because we're doing matrix multiplies, and it's really bothersome to try to change your matrix multiply for each image if it's not all the same shape. And then we're going to come down, again, normalizing data. See, again, most of the work is just getting your data in the right format, which you guys are already familiar with because you have to do that for Con, you got to do that for AFNI, you got to do that for FSL. Everything requires you to do that. That part hasn't gone away. Except now we're doing, MRI images here instead of those digits. And then when we get to the machine learning model, you can see we're using bigger images. So the machine learning model is bigger, but it's the same basic blocks. It's just convolution, normalization, convolution, normalization, convolution, normalization, with an encoder and a decoder. So same basic structure, and then it does some training, and we plot the loss, and we save the model, and we predict on data, and so then we do reconstruction of the test images, and we can denoise these. Another fun use for these is you can train it on a bunch of normal looking data and then test it on abnormal data and subtract the difference between the reconstruction and your input data, and it'll give you a map of the abnormalities because you trained it to reconstruct a normal. It's like you are training a sketch artist to only draw cartoon characters, and then you describe it a real person, and the sketch artist draws them to look like Luigi, and then you can tell the difference between what, a cartoon character and the actual person looks like, that kind of thing. So yeah, so that's basically it. That's what Ravi and I are doing every week in the Data Science Club, is we're trying to take an example like this that is really straightforward, really applicable to actual things that we do here on campus, but also approachable from the standpoint of, if you can open up Chrome, you can do the tutorial. And if you struggle with any part of it, Ravi and I are here to help. So just come to office hours or shoot us an email. That's what we're here for.
Can I ask just a dumb question about the Data Science Club?
Please do.
We've been doing a lot of T32 applications and applications for other stuff for students, and classes are an important component of that. Is there a class number or an official documentation of this class that we could put in applications? Because this is a rigor and reproducibility thing, which is required for NIH grants. And everybody in this room who's doing NIH grants should be talking about this in the grant, I think.
Okay. There is not yet official documentation on this. I would be happy to get that going. I don't know where to start on that. So if you know where to start on that, then let's follow up and make that happen, because this is something that when Ravi and I have talked with this pretty much across campus, every group is like, oh man, we need a computational training in our group, and this will kind of suit that purpose.
I have a dumber question.
All right, let's hear
When
it.
you say it's a data science club, there's actually like meetings for this.
So this is
Secret handshake.
yeah. So we'll work on the secret handshake later, but for the moment, what we're doing. So we recognize that everybody's time is valuable. It's difficult to figure out when everybody on campus would be able to meet once a week to do this, and between Ravi and the rest of us, we already have like almost 10 hours of office hours in a week, and that's like a quarter of our week. So it's like, and then we have the monthly user training sessions on top of that. And this work is best done on your laptop. And like the format that we did today, where you're sitting and listening to us talk about it, is less optimal than you actually trying to work on the code first and then hitting a stuck point and then going and looking at the video. And so that's what we're trying to do. We will, in the future, get it set up to where there's a set time during the week. So if you wanted to get on there live and watch us do the notebook, you could, and comment while we were doing it. But for the moment, what it is it's just we're figuring out the email situation of how to get it sent out. But it will just be a GitLab link or a link to a repository or a demonstration, and then a YouTube video of us struggling through that same demonstration, and then so that you can see where those struggles are and work through them.
Yeah, we have. I know this isn't just for the neuroimaging community, but like we have student meetings, which maybe the students here could create a little community and watch the videos during this time.
Yeah.
I think it's like the first Friday of every month. So maybe like on our end, we could create something of it.
Yeah, and that's totally awesome. What we're trying to do is get it set up to where even if you're not running through the code, we're creating some content to where you can, while you're drinking your coffee and reading through articles or something like that, you can even just put on the YouTube video or look at what the YouTube video was about and see, I could kind of see how I could use that, and then maybe run through the code and just try to get people more familiar with the terminology, more okay with actually running this stuff themselves and all that.
Yeah, the basic idea is that in a week there would be 1 hour where you'll be concentrating on data science, because everyone wants to be working on machine learning, but then the week comes and there is this task and another task and you just forget about it. And this will give you an hour where you can actually work on some data science and machine learning and gain more knowledge.
Yeah, and I mean it's as much for us as it is for you guys because this is the technology that is just really highly in demand right now, and we have the hardware for doing this, and so a lot of people are coming and asking us to do this work for them, and you know, it's much easier for us to get it set up of like, all right, let's start teaching people how to fish so you can go out and do some of this work on your own, and then we can collaborate more easily that way. And then hopefully over time we'll also learn the folks that are really particularly good at this, so if there are more involved, bigger, scary projects that need this kind of stuff, then we can say, okay, well, you really need to talk to this guy over here in computer science and stuff like that. Yeah.
Thank you.
Yeah, my pleasure. Any other questions?
Does that offer?
You have to talk.
Auburn, do you have any questions?
No, we don't.
Right.
Great.
All right.
All right, thank you.
Thank you.
Thanks so much.
Yeah, thank you.
And so is this, you said